What are the different electrical behaviors between different compounds? How does resistance, atomic structure, electron behavior, and heat all play into the conduction of electrons? Well, the first place I thought we could observe this is in a power management facility. So let's go there. Right now we have a live feed of the power management facility. This is where they determine how much energy to feed into the electric grid system. It's all fed through this one massive wire. But what's important to us is what's within the wire, pure copper. It has one of the lowest resistivities in metal, which is why it's used. Let's take a trip inside. First, let's get into what resistivity is. Resistivity is the inhibition of a flow of electrons. In order to really understand what that even means, let's look at how electrons flow throughout a wire. As you can see, electrons don't all move in one direction. They mostly move randomly, both backwards, forwards, up and down. They really are unpredictable. Although it may seem unpredictable, there are a few things that we do know. For example, between these metals there are metallic bonds. The special thing about these metallic bonds is the small amount of energy required to move electrons past them. Here's an example of how it works. As a new stream of electrons are introduced, they come in with energy. And with that energy, they break the bond of an electron in front of it, which then breaks the bond of another electron, and so on. These electrons are so loosely held to the metals that they are called delocalized electrons. This creates in a way a wave of electrons, which can be perceived as a stream if you add enough electrons. But the reason we are going over this is because it takes different amounts of energy to break away electrons from different metals. The stronger the metal holds onto the electrons, the harder it is for them to flow, causing more energy to be required just for them to pass through. This is what is known as resistance. Resistance also leads off to heat, since the movement of electrons really is just a transfer of kinetic energy. Think about it like this. When you rub your hands together, the reason you feel heat after a while is because of the friction that is attempting to slow your hands down. Metals feel the same thing, but instead of friction, they experience resistance, which is continuously slowing them down on their path. This is extremely important for places like power management facilities because if their wires put off too much heat, they self-destruct and nobody gets any power. However, before we get into how we can change the resistance via different compounds, you can actually change the resistance based off of the size of the wire through the use of the resistance equation. So this is the resistance equation. As you can see, you have resistivity times length divided by area. What this means is the resistivity of the metal, right? How easily or how difficult it is for electrons to pass through changes, and depending on the metal you have. And if you increase your resistivity, your resistance obviously increases. If you increase your length, there is more distance your electrons have to travel, which means you need more energy in order to get an electron from over here to here. And the final thing is area. So something we have to keep in mind is with area that whenever an electron is passing through, it's not going straight through. As we saw before, electrons can go up, they can go down, they can go left, right, up, whatever, right? So if you have more area, that gives more freedom for them to flow. But if you have a tiny area, they only have one direction, and the chances that they're gonna go in that one direction it's very low because electrons are random. So with this, you're restricting the randomness, and that causes you to require more energy. So in theory, the most conductive or least resistant wire would be a wire with the least amount of resistance, that is very short, and it has the largest amount of area. But then this is not even a wire, so yeah. These rules are the very reason why we have a thick wire in the first place. The thick wire provides more area and less resistance, which allows the electrons to flow more freely. When it comes to semiconductors though, there's a different way of decreasing resistance other than this. It is called doping. Semiconductors are similar to regular metals in the way that they allow for a flow of electrons. When it comes to doping, it is basically a way of decreasing the amount of energy required to get an electron to pass, and you do it by quote-unquote doping the silicon with another type of metal. You can either use N-doping or P-doping. N-doping requires a compound, usually phosphorus, that has 5 valence electrons. The doping of phosphorus into silicon creates a substitutional alloy, with phosphorus taking the place of many silicon atoms. And because silicon only has 4 valence electrons, being in the fourth group, compared to phosphorus's 5 valence electrons, the extra electron is easily taken away from phosphorus and causes a free electron to flow. The phosphorus acts in a way as a catalyst, but rather in terms of activation energy for a reaction, it just lowers the required energy for an electron to flow throughout a wire. P-doping requires a compound that has less valence electrons than silicon. When put in a mixture with silicon, it also creates a substitutional alloy in which boron or indium would take place of the silicon. Unlike N-doping, this form of doping, rather than providing electrons, takes electrons from the surrounding silicon bonds. This creates a difference in charge, which causes the electrons to move naturally. The electrons are pulled out of their stable bonds in order to fill the positive gaps, and these positive gaps move opposite towards the direction of the negative electrons. It's like how when you run in sand, you move forward, but you kick the sand behind you. You are the electron, and the sand is the positive gap caused by boron. This works in the same way as London dispersion forces as well. It probably takes a bit more time for probability to take its course and for all of the electrons to move in the same direction.